Hello, my name is Yuzhen Zhou from University of Nebraska-Lincoln. Today I'm going to present joint asymptotics for estimating the fractal indices of bivariate Gaussian process. This is joint work with Dr. Yiming Xiao. In this project, we consider a bivariate stationary Gaussian process X. It has two components, x1 and x2, which are defined on the real line. We assume the mean are zeros, and it has a matrix value of the covariance function C of t, and in the diagonal, the C11 of t and C22 of t mean the covariance function of the process x1 and x2 respectively, and in the off diagonal, the C12 of t and the C21 of t mean the covariance between the component process x1 and x2. And in order to study the smoothness a property of the process, we first of all assume the local behavior of the covariance function. For process x1, the C11 of t is when t is close to 0, it is equal to the sigma 1 square minus C11 times the absolute value of t to the power alpha sub 11 plus a small o of the absolute value of t to the power alpha 11. And here, the alpha 11 is a smooth parameter. It's determine the fractal index of the process. Similarly, we'll assume the local behavior for the process covariance function of the process x2. We use the parameter alpha 22. And here we assume the two component process x1 and x2 are not independent. They have dependence. So the C12t and C21t has a non-zero correlation rho, and also the local behavior, we use a parameter alpha 1 to describe it. And for a multivariate process, the covariance function should be positive definite. So we have some restriction of those for those parameters. Either the average of alpha 1 1 and alpha 2 2 should be less than alpha 1 2, or if they're equal, then the corresponding there's another restriction on the other parameters in the assumption too, like those constant and the marginal variance. So what we are, the assumption seems restricted, but actually a lot of models and applications satisfy our assumption. For example, bivariate Merton models introduced by NATE in 2010, or bivariate Pauli exponential or bivariate Cauchy models, all those satisfy our assumptions. And what we are going to study, we can take a look about these two trajectories. The first one is the trajectory for the process x1. Here we simulated a bivariate Merton process. When in the first process x1, we pick a small smoothing parameter, so the trajectory looks very rough, right? And in the second plot, we used a smooth parameter 0.7, so the trajectory is much smoother. And as we know, we got a feeling that when we are trying to estimate the smooth parameter is really related to the trajectory of the process itself. But the interesting question is, if the two processes are dependent with each other, for example, see there's a rho right here. Rho means the correlation between x1 and x2 at the same data point. If they're dependent with each other, will the estimator, the performance of the estimators be affected by the other process or not? So this is what we are interested in. So here's the setup. So we consider the estimators of the smooth parameter alpha 1 1 and alpha 2 2. We want to know how would the cross covariance structure affect the performance estimators. To this end, we study the joint asymptotic properties and the infield asymptotics. And the infield asymptotics means we consider data observations in a fixed interval. When the sample size increases, that means that we have more observation in the fixed interval. There's a lot of literature working on the univariate random process to study the estimation and inference for the smooth parameters, such as the variable method, box counting method, spectral method, and the increment-based method, or higher order quadratic variation method. And here we mainly follow the increment-based method introduced by Kent and Wood in 1997. And the basic idea is we look at for each trajectory process, we will take the difference of the process at different, let's say, different time points, like L over N, L minus U over N, or L plus U plus over N. U is considered as a lag of the data points. So when we take the difference and calculate the variance of the resulting statistical Y, we found out that the variance converges to a constant times the lag U to the power alpha I. From there, it's easy to derive a statistical estimator. What we can do is, okay, we define Z as a square of the Y, then we take the average of those Z, we call the Z bar. And by the law of large number, we know the Z bar converge in probability to a constant times U to the power alpha I. And further, if we take the log of the Z bar and the U to the power alpha I, we got a kind of linear model. So we can see that the smooth parameter can be estimated by in a regression model. So we can either use the ordinary least square estimator or generalized least squares methods. And in 2000, Chen and Wood, they extended this idea to construct a general linear estimators for the smooth parameter. And in our later theoretical framework, we'll use this estimator. So alpha I hat equals to a linear combination of a sequence of constant L with the log Z bar. And we have some restriction on the L. The summation of the L should be 0, and the linear combination L and the log U should be equal 1. And both the OLS and the GLS estimator we mentioned, and which were introduced by Kent and Wood in 1997, are examples of this estimator 7. So in order to do that, we know Z bar is very important. So first of all, we put them together. For the Z bar for the process X1 and the Z bar for the process X2, we put them together and we define a Zn bar, and we study the covariance of the Zn bar and the symptotic property of this. And in order to derive our theorem, we give another like a regularity property, which also, again, all those previous mentioned examples satisfy those conditions, which we call condition A2. So theorem 1 tells us, if we standardize the Zn bar and scale it by square root n, asymptotically it converges to 2m dimensional normal distributions with mean 0 and the covariance matrix of 5, 0. An interesting finding is that when the average of the alpha 1, 1, alpha 2 less than alpha 1, 2, then the covariance, the asymptotic covariance between the Zn1 and the Z bar and the Zn2 bar is converged to 0. So which means, okay, asymptotically they are independent. Also, although the process X1, X2 are dependent on each other. So then we're interested in if this property will eventually appear in the asymptotic property of the estimator of the alpha 1, 1 and alpha 2, 2. So we make a stronger assumption by specifying the remainder terms in assumption 2. In assumption 2, we just give the first 2 terms. We don't specify the remainder term here. In order to get a simpler form, we make some more specification on the expansion of the covariance function locally. And with this condition, we found that the bias of the alpha I hat is big O of n to the power -1. It's like a regular efficient estimators. And the mean square error matrix, we know that the marginal variance of alpha 1, 1 hat and alpha 2, 2 hat, they are still kept at big O n to the power -1. But the covariance between the alpha 1, 1 hat and alpha 2, 2 hat, it's different. It has 2 scenarios. If the average of alpha 1, 1 and alpha 2 equal to alpha 1, 2, then it's still at big O n to the power -1. But if the average of the alpha 1, 1, alpha 2, 2 less than alpha 1, 2, then it's a small order of n to the power -1. And this finding eventually leads to our last theorem. So if we standardize the estimator and times the square root of n, eventually it converges to a bivariate normal distribution. And we find out that if the average of alpha 1, 1, alpha 2, 2 less than alpha 1, 2, then the alpha 1 hat, alpha 2 hat, if you multiply by square root n, they are asymptotically independent. And this means if there are, if although the process x1 and x2 are dependent on each other, as long as the average of the smooth parameter less than alpha 1, 2 is the decaying rate for the cross covariance function. If this is true, then actually the performance of the estimate alpha 1 hat and alpha 2 hat will not affect with each other, will not be affected by the other process, although the two processes are dependent with each other. And eventually, we can show you a simulation. We simulate a bivariate Matern process with different sample size. Want to see how the decaying rate looks like. Okay. So first of all, these two processes show you the confidence interval, and we can see actually the estimator is quite good. The confidence interval is quite narrow, and then we show the bias. We know from the theorem the bias has an order of big O n to the power -1 in either case. So this looks fine. So they have a decaying rate at n to the power -1 in both cases. And but the mean square error matrix, there's something different, right? We see that the margin variance still keep in the order of n to the power -1, right? But the cross covariance is different. The cross covariance for the case, if the nu11 equal, the average of nu11 equal to nu12, then it decay at the rate n to the power -1. But if the average is less than nu12, then you can see it decays much faster than n to the power -1. Actually, in this simulation, it's about n to the power -1.5. And that's all. Thank you. And the details about paper, and we have more general theorem. If you're interested, you can take a look at the paper, which is posted in the archive. Thank you.